Thank you very much for the introduction. I'm happy to be here to contribute to a compound semiconductor and explain how AIXTRON is supporting that and to make it happen, as mentioned. So I will quickly have a snapshot on the compound semiconductor market and how we see the contribution, and then looking to what AIXTRON solutions are helping to boost gallium nitride in the semiconductor. So we have seen multiple reports looking into different applications, and a lot of things was mentioned already today, and we see that here reported by you that there's more than 2x increase of the market size of the compound semiconductor market. And if I look into what are the key drivers for that, and I see three mega trends. On the one hand, we have CO2 emissions reduction and electrification. So how can we make best use of the electricity we have, so increase the efficiency of our devices, and so that we can convert the electricity very efficient from one situation where we generate electricity to where we use it. On the other hand, we heard a lot about AI and to feed all the CPUs, GPUs, who do all the calculation which we need to get a better life-work balance, which I understood. And this is where we see that gallium nitride can play a role, right, in different applications, from serving 650 volt application down to 100 volt application mentioned by TI here. So therefore, a lot of things where gallium nitride can support in the industry. And I will now have a deeper look into how we support the gallium nitride power industry in that regard. So let me first start with what we're doing today, the HVM solution for 150 and 200 millimeter wafer size. So I was very happy. Last year, I introduced our next generation, the G10 GaN, right? And we had a very good feedback based on your utilization, customers using their tool for their volume production of gallium nitride. And the key change, what we introduced last year, was that with our G10 GaN, we can boost the yield by improved uniformity, and we can improve the reproducibility of the production, so that we make sure that every device, every wafer gets the same quality over very long campaigns. And very important was that we reduce the cost per wafer. And from a previous generation to the G10 GaN by more than 25%. And this is what I introduced last year, and we had a good rollout now, which is starting with the G10. But the question is, what's coming next? What is AIXTRON working on to further improve, what further help you in that introduction of GaN in the market? And what we're doing is we're continuously looking into further cost down activities to help you to lower your cost in production, and therefore to boost the penetration of gallium nitride devices in the industry. So let me quickly go back on one slide on what is the technology what we serve. So what we do is we have a horizontal reactor where we have the gas flowing from the center to the outside where it's where the exhaust is. And the key technique what AIXTRON is doing is that we have an individual rotation of each wafer, so that we can calibrate each wafer one-to-one in terms of temperature and performance. And this double rotation enables a single wafer performance in a batch reactor cost benefit. And this is really the core of how we enable mass production in a very reproducible way. Now, I mentioned the G10 GaN can deliver excellent epi quality, excellent uniformities, And here a snapshot of typical results which we can achieve, where we have thickness uniformities which are lower than 1% standard deviation. And in particular, the very important active layer is the gallium barrier, where we can achieve ranges of thickness below 0.5 nanometer and composition uniformities lower than 0.5%, which really helps to define the advanced specification for the GaN devices, which is necessary for high yield on that side. Now, if I look into here, this is the EP side, so what you can measure based on that. But important is how does it is reflected in the device characterization. And AIXTRON has no own device line, and therefore we work with partners to characterize our devices, our structures, to make sure that the improvements and the changes we're implementing are valid not only on EP level but also on device level. And what I show here is that we work together with Belgan here, where we could demonstrate here on a 6-inch wafer excellent uniformity, and we could even improve the threshold uniformity from the previous generation to today's G10 GaN relation by more than 30% over the full wafer. Now, it was mentioned, there was some question on how we can get reliability testing, right? This is a very important aspect to boost GaN application in the market. And therefore, we also looked into how does the devices which we get are get reliably on a wafer level. And here a snapshot of a couple of results we have obtained. So the buffer dispersion at high temperature and the high temperature burst bias reliability testing, which shows that we really have excellent performance here if we apply a stress to the wafer. So it really shows that the EP quality, what can be obtained by our tool, gets excellent device level. But it also shows, and this is also important for us, that our BKM, our best known method, our base structures which we use for the qualification of our tool, are matching a certain base level of device performance. And this gives us the possibility to really judge on any change, any improvement we're doing, because we know that our structures are deliver the necessary level of performance. Now, I talked about cost reduction, and we delivered with the G10 GaN a 25% reduction against our G5 Plus, right? So a significant cost down, which is here the leading MOCVD reactor in terms of cost per wafer. And we have obtained that by having improved equipment uptime. So we worked a lot on how can we reduce the number of interactions with the tool by having a very long time where the tool is just running in a run edge mode, where we reset the reactor hardware after each run. And on the other hand, we use these long lifetime consumables, which is extending the maintenance frequency on the one hand, but also reducing the overall cost of the work per wafer. And last but not least, we have a very compact cluster design, therefore we can share up to 3 process chambers with one handling system, which makes the tool very compact. And on the other hand, very effective in terms of CapEx cost per wafer and CapEx cost per square room in terms of throughput per fab area. But what's coming next? We have now worked on further optimizing based on the G10 GaN to further reduce our cost per wafer. What did we do? We focused on all the non-valuable time in a full cycle. So typically what you do is you load a wafer, then you do EP, you unload the wafer, you do a quick cleaning, and then you restart. And what we focused on is especially these non-EP time, this non-productive time, because you're not depositing materials. Here we significantly reduced the cleaning time. We optimized the handling procedure to to have a more than 10% throughput gain, and this gives a significant improvement. On the other hand, we worked on further improving the maturity of the tool after the product launch, based on the feedback we got from you as a customer in terms of using the tool, which is then helping to have a better utilization of the tool. And last but not least, we have seen that our long lifetime components even are outperforming to our expectation, and this is now the feedback based on the multi-years implementation and use of the tool in mass production, where we can now go to a next level of performance. And altogether, this then ends up being in the range of 10% cost reduction, which we can deliver from last year to this year. And this is already a big achievement. Nevertheless, the question is, what do we do for the different applications? Because here, I mentioned this is an example for a 650 volt, and I also highlighted that here we worked in particular on the non-Epitaxy. But we see also a big potential in how can we optimize the Epitaxy. So the question for us as a manufacturer of an equipment is, what is the limitations we have today on our equipment, which we have to overcome to enable faster Epitaxy? And this is what we look now for all the different applications very systematically in a dedicated throughput improvement program, where we try to increase the growth rates, therefore decrease the overall epi time in order to boost the throughput per tool for the different applications. And here, as mentioned, we use partners to validate our improvements. And based on the good feedback we get is that if we here predict by the end of 25 overall 34% higher wafer output per chamber compared to today, that means we are confident that based on our results that the quality of the epi material is not degrading by this change that we're doing. And this is here an example for 650 volt, and this implies the shorter cleaning and faster transfer that I just mentioned, but also here a reduced epi time by increasing high growth rate and optimizing heat ramps in the epi process. Going further now to low voltage application. I think TI mentioned all the different voltage classes, and typically you just scale down your epi thickness, which is scaling down your breakdown voltage. But I think important is that, especially for the low voltage application, we looked into how the typical process looks like, and we have ideas which can significantly reduce the throughput by optimizing, especially the initial growth on silicon, which takes a lot of time right now. And we are working on a fundamental difference here, which can boost the overall wafer output by more than 70%. So it's really something where we try to help guiding you as a customer and then sharing that know-how with you, how you can boost your production with a given tool, which is a G10 GaN, which is now here available on the market. Last but not least, what about high voltage? And here again, we also look into more applications which go into the automotive industry. So here the requirement is, can you scale up the breakdown voltage to 1200 volt and beyond? And also here, we're trying to establish a certain base structure by scaling up the thickness profile and the thickness stack, and achieving breakdown voltage which are far beyond 1200 volt. So therefore, we demonstrate that the G10 GaN can deliver the necessary epi performance for all the different applications which are in R&D or in production today. Now, this is all up to 200 millimeter. And there was a question for the TI colleague, what about 300 millimeter? And yes, we're also working on that. What are we doing? We're using a different kind of technology from AIXTRON, which is a vertical technology, so-called our closed couple showerhead technology. So what we do is we deposit, we have a flow from the top to the bottom, and what we use is here a single wafer reactor, where we have one 300-meter wafer, which is sitting here in one chamber. We have a showerhead delivering a uniform gas flow over the full wafer. So therefore, out of the box, you have a very uniform deposition. We have a lot of tuning knobs, a lot of optimization possibilities, because we can adjust the gap between the injection and the deposition, which can be very important for different process regimes, different materials, different applications. And with our multi-zone temperature heater, we can modulate the temperature over the full wafer at any time during the process, which is extremely important for this large wafer, because we have to take care about the stress. How can we manage the stress of the wafer during deposition? Because in the end, you want to have a very flat wafer after the deposition process. And we use the known technique, which is our CO2-based cleaning approach, to reset the reactor after each run, because this is important for reproducibility, and this is also important to have a fully automated tool. And this is what we then here provide is a full front end. So there's no touching of any wafer. Everything is done fully automated, which is necessary, especially for these very sensitive large wafers. And if I look now into what kinds of early results do we achieve uniformities and composition uniformities which are similar or even better what we achieve on our 200mm platform. Yeah? And here's an example of a low voltage stack, which is in the range of 1.9 something micrometer, where we have standard deviation of the full 300mm wafer less than 0.4%, and for the lower thickness. If I look into the argon composition uniformity, we are in the same range as mentioned on the 200mm, which is the 0.5% absolute. And all that we achieve using semi-standard 111 silicon substrate, and achieving a wafer bow after a cool down and taking out of less than 40 micrometer, which is crucial for the subsequent processing in the chip. And in addition, important to mention is that we manage the stress to the wafer, especially in the initial heat up, native oxide removal, that we don't create slip lines in the wafer, which is very critical for processing. Also, the epi quality in terms of cracks is in a similar range of what you know today from your mass production on 200mm. So how did we come to this kind of structure on 300mm? And what we have seen is that we can very easily transfer our process stacks from the 200mm world to the 300mm world. What we do is, and this is an example of here the previously mentioned medium voltage stack, we just transfer the temperatures, we transfer the flows by scaling factor between the 200mm and 300mm, according to what is the flow per wafer area. We match the growth rate, and in the end we achieve nearly identical epi stacks. And this is what we're right now trying to do for all the different processes which I previously shown on the 200mm, and this gives us the possibility to really qualify that we have been successfully transferred early device from the 200mm to 300mm. And what we did is, what you can see here is, on the here a low voltage stack on 775 micrometers silicon. This is the 1.3 4 micrometer stack, which delivers a breakdown voltage in the range of 200 volts. So for low voltage application, this would be acceptable. Now, the question which we typically get is, what is the maximum thickness we can grow on semi-standard wafer? Because if you look into the processing line, it's always, you want semi-standard wafers, and therefore we continuously trying to improve the maximum thickness for those layers on semi-standard wafers. Right now we are in the range of 3.1 micrometer, which we can deposit on semi-standard substrate, which gives you a breakdown voltage in the range of 500 volt. But this is a very intensive work we're doing here to further improve the thickness on semi-standard wafers. If you want to prove that in general the process is working, what you can do is you can do to non-semi-standard silicon substrates. Example here, 1.5 millimeter thick silicon. And there, for sure, now you have a stronger substrate, and this enables you to have a much thicker silicon GaN EP on that silicon wafer. Yeah. So in the end, here it shows that all the learning, all the understanding of EP stacks can be one-to-one transferred from 200 to 300 millimeter. And this is where we're now starting to engage with customers very early to look into what kind of possibilities 300 would have for GaN production in the future. So let me summarize that we have two paths. The one path is what's happening today, which is the volume production on 150 and 200 millimeter. This is addressed by G10 GaN, and we have a continuous cost down roadmap in place to help you to further improve your cost situation. On the other hand, we're looking to, with our closed copper showerhead technology, into possibilities for 300 millimeter. Thank you for your attention, and we're open for questions.
Yes, please. Thank you very much for sharing. It's very nice, very exciting to see that the AIXTRON now is working on 300 millimeter GaN. So that's a very exciting field. But I wonder, so you have a single wafer chamber for 300 millimeter. That means you can only produce 1 wafer per ton. But for 200 millimeter, you have to produce 5 wafers per ton. So if you consider this throughput, in the end, 300 millimeter will have the cost advantage compared to 200 millimeter?
It's a very good question. So yes, if I go from a batch reactor to a single wafer reactor, the first impression is I will not be able to have a cost reduction. This is true in the first place. On the other hand, if we talk about volume production, then we talk about a compact cluster design. And this is something AIXTRON is working on, right? To be able to not have a single wafer reactor, but having a cluster design similar of what I've shown on the G10 GaN. So this enables then a more volume production environment. On the other hand, so my view is that going to 300 meter also enables cost reduction not only in the EP, but also on the chip processing line. So in the end, you have to look into the full production chain of your device, and there I expect that the cost down is possible.
Okay, thank you very much.
Other questions? So actually, yeah, we talked about the 300 millimeter tool, but have you ever evaluated, because the industry now is moving, gallium nitride and silicon moving from 6-inch to 8-inch, and actually the majority still, I think, is on 6-inch, and now it's moving to 8-inch. So when do you think the 12-inch tool will become popular for gallium nitride and silicon? 2 years, 3 years, 4 years?
I think it's more 4 years. So what we see is that if you look back, right, so gallium nitride also starts with 6-inch, and then it was moving a couple of years later to 8-inch. And so now we see the same again, right? We see, okay, the gallium nitride EP is following also the general trends of silicon, right, and also moved to 300 meter at a certain time. And therefore, we see that we have early customers looking into, can we do these synergies between their silicon fabs, which are running on 300 meter, and their GaN fabs. So can there be their synergies? And this is where we see that there are early investigations, And this is why we are here with early results, showing that there's a general feasibility, but it's still a long way to be in mass production. I fully agree on that statement.
Okay, thanks. Yes.
Just following your question, okay? So many 8-inch fab right now is producing for GaN power right now, right? That probably would take many years to go. So why do you think the 12-inch will come into the picture within 4 years? What will be that application? So the killer application to address on 12-inch.
So I think that it's difficult to say, right? I think what I see is that on the low voltage application, I see that here 300 millimeter can be something. If we talk about AI, it could be an application because you're not talking about only 650 volt application, which is for the general power supply of the GPUs, but also of the on-chip, right? If you go from 48 volts to 40 volts to 12 volts into 1 volt, right? This power conversion. And if you look here into that kind of low voltage application, I see that you integrate silicon mindset, silicon devices with GaN, and therefore we see players looking to synergies in terms of their production, in terms of wafer size. So that's one aspect. In the end, the question is if you can do volume production on 300 millimeter and you can achieve a certain cost reduction in terms of your processing, right? Because you have a like 30% cost reduction going from just the processing cost of a 200 mm wafer per area versus a 300 wafer, if you talk per area. And therefore the question is, can 300 be part of that long-term cost down roadmap? So I think there's a lot of things to explore, right? So therefore it's not proven, but I think it's the right timing to look into what could be the next step so that we can prepare these paths and therefore have a good future of GaN, right? So it's part of something which is not happening now, but we see early investigation to that direction so that we want to explore the full cost model of 300 GaN, and then we see how far we can push that.